This material is something that you have covered in a previous course. I don't even mean calculus. You probably did this in college algebra, pre-calculus. But let me just sort of remind you, we're only going to spend a little time on a couple of examples here. And let's take a look at what an exponential function could look like. Let me draw what happens here. That'll be, it crosses the y-axis when y is 1. And the function I'm talking about is y equals a to the x power, where a is some number greater than 1. You notice that it really climbs quickly after it passes the y-axis. On the other hand, we could also cross at 1, but come down and do the opposite kind of a thing. Same equation, y equals a to the x, where a is between 0 and 1. We never, in any circumstance, want to deal with a being 0, 1, because nothing happens. It's a flat line, and there's some continuity issues with 0 anyways. But you definitely don't want to do negative numbers, because then you'll start introducing complex imaginary numbers, and we're not working with those. So the point I'm making is these are the two models we're going to be using for everything. But what's nice about it is this. If I set y equal to a to the x power, you'll recall that you can rewrite this as e to the natural log of a to the x. And then I can bring the x down in front, or it really doesn't matter, but I'll bring it down. I'll have e to the x ln of a, and then I'm going to use a rule of exponents that says that I can rewrite this as e to the ln of a raised to the x power. So what I'm saying now is this here is my new base, but the important thing is it's e to a power, and maybe this is the one I want. This is the one that I want to work with more than anything. So instead of a to the x, we work with e to the kx. And all I need to do is a couple of examples to show you how this works. You won't have to memorize different bases for the problems you do. You just have one thing to use, and it works for everything. So let's do an example of what I mean. One of the most popular examples of what we're going to do here is something called half-life. So let me start with that. The half-life of a radioactive substance is 10 days. How long will it take to decay from 1 times 10 to the 9th grams to 100 grams? So and half-life, I think most people have an intuitive idea, and for the most part the idea is right. Here's what happens. After 10 days, we will have half of the mass of the substance less, which if you're on Earth and you're near, well, it doesn't even matter where you're near, that's most likely going to account to half the weight. It will start to just eject radioactive molecules as it's sitting there. So anyways, here's how we set these kind of problems up. Now, if I were to take the use of the a to the x method, I would try to do something like this. I would say, well, after 10 days, how much would I have? I would have 1/2 of the 1 times 10 to the 9th power, which is 0.5 times 10 to the 9th. And after 20 days, you'll have half of that. So I'll have 1/2 times 0.5 times 10 to the 9th, which is 0.25 times 10 to the 9th. And you can keep going and seeing that after 30 days, we have 1/2 of the 0.25 times 10 to the 9th, which equals 0.125 times 10 to the 9th. Now, how long is it going to take before we get all the way down to 1 times 10 to the 2? That's 100. How long is it going to take? And you can see this would be arduous, but you probably would trap this between days. So what I'm saying is this: we have information about it being 1 to the 10th or 1 to the 9th power to begin with. So let's say it starts at 1 to the 9th. I'll put a dot. I'm not going to label anything except for the days. And then we have 10 days. Well, then I have to be half that height, like so. And then you go to 20 days, and you get half of that height. And then 30 days, you get half of that height. 40 days, you get half of that height. You can see where this is going. You see, it does tend to look like a bent curve. If you follow along, I don't know where it was, but when I first started taking science classes of any kind, they would often tell us to connect the dots with either straight lines or with a curved line. For this purpose, I'm going to use a curved line to connect the dots. The nice thing about this curved line is that it's differentiable, very smooth, and I'm also going to be able to tell information in between these halvings. So this is not something you could do here. You would have to estimate, unless 1 times 10 to the second happened to be exactly on a time when you have half the amount. You'll be stuck between two 10-day periods, beginning and an end of a 10-day period, and you would just have to estimate them. This gives a much better, what we're going to do will give a much better approximation. So here's how it works. We're always going to set up the model looks like this. F of x equals c times e to the kx. I have two unknown quantities besides the variable x. X is a variable. K and c will both be constants, but they have to be figured out in the context of the problem. So when you look at this problem that we're doing here, how long will it take to decay from 1 times 10 to the gram to 100 grams? We know that it starts at a mass of 1 times 10 to the 9th. So we're going to let f of x equal the amount, let's call it the mass, of the object. After t days. So this is probably a bad idea to use an x. I think t is the better thing to use. And another piece of advice I want to give you, the problem was stated in days, so stick to days throughout the whole problem and you won't have to worry about any kind of changes later on. So if f of t equals the mass of the object after t days, what do we know? We are given that f of 0 equals 1 times 10 to the 9th. We know that that's how much we have initially. But if I'm going to use this model, f of 0 also equals c e to the k times 0. But that's c e to the 0, and e to the 0 is 1. So I know that f of 0 equals c. So that means my f of t then takes the form of 1 times 10 to the 9th e to the k t. Now before I actually answer the question, the next step is to find out the value of k. and you need one more piece of information, we do have a piece of information. We know that the half-life is 10 days. So f of 10 equals 1/2 times the 1 times 10 to the 9th, which, as I said, was 0.5 times 10 to the 9th. But on the other hand, f of 10 equals, now I already have the c, this is my formula right here, so I have 1 times 10 to the 9th e to the k times 10. But I'll replace f of 10 with this number. So there gives me the equation. 0.5 times 10 to the 9th equals 1 times 10 to the 9th e. It feels unnatural to write k10, so I'm going to write 10k. And then I'm going to divide by 1 times 10 to the 9th. Well, this turns out to be exactly 1/2. And then I'm going to solve for k. Anytime you have an e to something power, the natural choice is the natural logarithm. I'm going to take the natural log of both sides. And then the natural log wipes out the e. And I get 10k equals the natural log. I'll write 0.5 because ultimately I'm going to a calculator anyways. Divide by 10. And you can even make it really short and sweet looking by simply writing 0.1 ln 0.5 equals k. That'll keep everything on one line. So now I've got everything I want. I've got f of t equals the c that we found from before was 1 times 10 to the 9th. Then I have e. And then my k is this stuff right here, 0.1 ln 0.5, all of that stuff, times t. Now the question is, how long will it take before I get to what? What was it asking me? How long will it take to decay to 100 grams? So what I want to know is t equals question mark when f of t equals 100. So I'm going to replace f of t with 100. And I'm going to try to solve this equation for t. So the first thing you'd want to do is divide by that. So I have 100 over 1 times 10 to the 9th equals e to the 0.1 ln 0.5 times t. Now this side over here is interesting. Instead of the 100, if I thought of this as 1 times 10 to the 2, I will be left with 1 times 10 to the negative 7 equals e to the 0.1 ln 0.5 t. Now you can finagle this stuff around to make it work out, or just take a natural logarithm, natural log of 1 times 10 to the negative 7 equals natural log of this side. And it'll wipe away the e. I'll be left with 0.1 ln 0.5 times t equals ln 1 times 10 to the negative 7. And finally, I'll divide by this stuff, the 0.1 ln of 0.5, to give me ln 1 times 10 to the negative 7 divided by 0.1 ln of 0.5, and that will equal t. And when you do this computation on your calculator, you should end up with about 233 days. We'll call this an exponential model. And it will look like, I'm going to use the letter A because it will more often be the amount of something. And instead of a c e to the kt, I'm going to write an a of 0 e to the kt. What they call this amount here is the initial quantity. Or initial value, whatever you want to call it. But the important thing is this is the thing we are going to use for everything. Whether we increase or decrease, I can use this one model for everything, so I don't have to memorize or try to figure out anything as far as half-lives, or even if they gave fourth lives or third lives, which I don't think they do, but if they did, this would handle it. It also handles growth, like I'm going to show next. Ben Franklin left $2,000 to the, well, let me see, $2,000 total to the cities of Boston and Philadelphia when he died. He didn't die in 1790, but that is the interesting date. When he died in 1790, he wanted the cities to distribute the money 200 years later, but the money was allowed to accrue compound interest for 200 years. So, if the money earned 5% per year, how much was there? In 1990. So that's when they were supposed to start giving the money out to young printing apprentices and things of that nature. Well, let's take a look at this 5% here. What does this 5% per year mean? It means what we start with $2,000 as our starting value. So let's say year 0 and amount. Well, after 1 year, this will now be worth 2,000 times 1.05. That's how you accrue 5% interest plus the original amount each year. So I believe this comes out to be 2,100. And then the second year would be 2,100 times 1.05 again. You see, this interest is compounding. It's compounding. It's not just interest on the original amount, it's also interest on the interest. So whatever this turns out to be, we'd have 2,100 plus 5 times 2,100 would be 120. So you see, it made a little more money than the year before, etc. Doing it this way would be a pain, although when you get to year K, you're going to have 2,000 times 1.05 to the K. And you could use 1.05, you could use this as your model, but then again, you're doing a specific number for each different type of problem. Instead, let's model it this way. A of t will equal A of 0 times e to the kt. That doesn't mean your k is automatically 0.05 or 5%. That is not what that means. what are we going to have here? Well, I already know a of 0 was 2100. And I also know that after 1 year, that a of 1 was equal to $2,100. And a of 1 equals 2,000 times e to the k times 1. So I'll set these two equal to each other. I have 2,100 equals 2,000 e to just the k. I'll divide by 2,000. You don't have to simplify, but I can. 21 over 20 equals e to the k. And then I'll just take the natural logarithm. Leave it at that. You could. 21 over 20, guess what it is? This is ln of 1.05 equals k. So what I have then is a of t, I've got the complete formula for it, is 2,000 e to the ln of 1.05 times t. And then, of course, we want to find out how much it's going to be worth after 200 years. So our answer then is a of 200, which equals 2,000 e to the ln of 1.05 times 200. Notice the original information was given in years, so everything is written in terms of years. You could, as I said before, you could play games and put this 200 up there and have it simplify, or just let your calculator do the whole shebang right now. What you'll end up, actually, I shouldn't say approximately, because when you're talking about money, you automatically stop at 2 decimal places of accuracy. Banks do that no matter what the 3rd and 4th decimal place are, but they may round up or down. I don't know. All I know is this one comes out to about $34,585,161.63. It turns out that problem is solved, so we're done. Let's put a check by it. It's finished. But I want to sort of tell you what actually did happen. It turns out that there was only $9 million. Roughly. I'm sure there were some dollars and cents or whatever. But roughly, there was only $9 million in 1990. Okay, so if he didn't get 5%, this obviously he got less than 5%, because this is way short of $34 million. So it's only $9 million. No, nothing to sneeze at, but still, $9 million is way less than $34 million. What kind of an interest rate did he get? So what was his interest rate? Well, let's see what happens here. We still have this thing, a of t equals, we don't have the 1st and 2nd year, but we do know this. We still know that it's a of 0 times e to the kt. We do know a couple of things. We know still that a of 0 was $2,000. But now, instead of the 2nd year being $2,100, we do know that the 200th year, we know that a of 200 was $9 million. So what I can do is plug a of 200 into this equation and set it equal to 9 million. So I'll have 9 million equals 2,000 e to the k times 200. I'll divide by 2,000. I'll rewrite the top as e to the 200k. I'll do a little simplifying here. 9,000 divided by 2 is 4,500. Of course, once you get to this, you know that you take the natural log of both sides. Divide by 200. Don't you dare try to simplify this thing. This 200 cannot cancel with anything inside of that natural log. You just have to live with this number. So, what kind of an interest rate did Ben Franklin actually achieve? Here's how we figure it out. What was the interest rate? I should probably say, what was the actual interest rate that he got? So the easiest way to do that is to figure out what A of 1 was. A of 1, we still had the 2,000 e to the k times. So after 1 year, this number to 2 decimal places was 2085.91. Now, how do I figure out what the interest rate was? Well, it's easy. The interest rate you can get by taking, because it's the same interest rate from year to year, I could do year 1 versus year 0. In other words, 2085.91 divided by 2,000. And I get, if I'll stop the decimal places at 6 digits, I think, 1.042956. So can you see what the interest rate was? Let me come back a little bit. Let me go up a little bit to one of the previous parts we looked at. Do you remember I told you the original problem had a 5% interest rate, and I looked at year 1 versus year 0, and I got 1.05, and there it is. After the 1 point, the rate is staring you in the face. So right there it is. That's the rate. We'll call it int rate. It is approximately 0.04956, or I'm missing a thing here. There's a 2 in there that I forgot. Let me change it to a percent. There was our final answer, but I want you to see something even more important. This roughly 4.3%, a little less than 4.3%. A little less than 4.3% earned us $9 million. However, for just 0.7% more, it shot up to almost $35 million. Just 0.7% did all of that, because the length of time was 200 years. So you can see this is the speed with which things grow is intense. But this is really all there is to it. Any problem that you have dealing with exponential growth or decay can be modeled with this kind of a formula. And you'll need the initial amount, which is almost always given. If not, you can always, as long as you get 2 amounts, you'll be able to solve for whatever the C was out front and whatever the K was, because you'll have 2 independent equations and 2 unknown quantities. But as far as I'm concerned, I'll be dealing with this kind of a format here. I think it's good enough for to tell you the power of exponential modeling.